Hello class. So today we're going to be talking about the relationships between the tangent line. So relationships between tangent lines, or we'll just say tangents, and the circle. Alright, so there's some relationships between tangent and circle, or parts of the circle, whether both inside and outside of the circle. So that's what we're going to talk about. We're actually going to prove those relationships and then utilize them in another video. So the first relationship that I want to talk about, I'm first going to just draw it so you can see what it is. If I have a circle and a tangent line outside of the circle, right, meeting at that one point of tangency, then there is a radius to that circle that'll meet at that point of tangency where it will in fact be perpendicular. So that is the relationship, that this tangent line is perpendicular to this radius that meets at that point of tangency. And if I could theoretically go on the other side and draw another tangent line, there'll be another radius there, and I can do another tangent line on the bottom side over here, bottom left, and it'll also be perpendicular. Let's go ahead and prove this relationship. So this is the relationship right here, that the tangent is perpendicular to the radius in short. And that's what we're going to prove. And we're going to prove it using that style that we briefly discussed, the indirect proof. Maybe about a month ago we briefly talked about that, the indirect proof. Let's go ahead and do that. So I'm going to draw another circle, and I'm going to show you indirectly that this is the case. Oops. So this is the proof right here. So let's give ourselves a circle, and then let us assume that there is a tangent line outside of this circle. I'm going to draw another line. So there's my tangent line. And since there's a tangent line there, then there is going to be a radius that's going to touch at that point of tangency. But this time what we're going to do is we're going to assume the tangent is not perpendicular to the radius. That is the assumption, that it is not perpendicular. If in fact it is not perpendicular, then I can come up with some other things. And there must, first of all, be someplace else where there's a line that can come from the center to where it can be perpendicular to this line. Now, part of this, we don't go off of how things look, but if you take a look here, you can see that that in fact would not be perpendicular, but we're going to make it perpendicular for the sake of proving our point here, right? So this one is not, this radius is not perpendicular, but this other line is the perpendicular one. Let's give these points, we're starting to end up here with a whole lot of points. Let's give everything a name. So let's say that this was circle O, and that this point of tangency is P. So OP is not perpendicular, but OL is. Alright, now OL is perpendicular, and there is some other line out here. Let me undo that one and give ourselves a perfect line. There we go. There's another line out here that I can sketch, and the purpose of me sketching this other line is so that LP is the same length as L. Let's give this letter named K. Say LK. So LP is the same length as LK. If that in fact is the case, then what you have here is a situation, you got this big triangle, but really you have two smaller triangles that are going to have to be congruent to each other. Well, how do you know they're congruent? Well, they're congruent because of this. I know that triangle OLP will have to be congruent to triangle OLK by side angle side. OL is the same shared side, so that's reflexive property. They are congruent. Then LP and LK are congruent because I set K to be the same distance from L as P was from L. And then the two right angles, because we set OL to be the perpendicular angle, then the angle inside of there, those two angles are going to be congruent because they're both right angles. So if that is the case, then all other corresponding parts of these two right triangles are going to be congruent. So let's say OP out here then, right, OP would have to be congruent to OK. That would have to follow by CPCTC. Corresponding parts of congruent triangles are congruent. All right, now here's our contradiction. Here is our problem. This is a contradiction. And I'll write that down. This is a contradiction because I can't have this piece right here congruent to this piece right here. For one, OP is supposed to be the radius. Well, if OK is congruent to OP, that would make OK also a radius, which would mean that in fact that the line that we're looking at does not touch at one point. It would in fact touch at 2 points, making this another type of line, making it like a secant line. So it's really not this line that we're looking at here. So that is our contradiction. So the indirect proof says that if wherever we started or wherever we made our assumption, we have to go back to that point and reverse it. So we started with the fact that OP was not perpendicular. Everything else that we did from there was mathematically legal, you could say. So we go back to that point where we made an assumption. And so our assumption can't be true, which means that we must take the opposite, that that tangent line, in fact, must have been perpendicular at the radius. All right, great. Let's go ahead and do our second or prove our second relationship here. Our second relationship will follow just from this one, and we can quickly go through it kind of time. So our second relationship is this. Let's say I have a circle, and I'm going to go ahead and draw the relationship that I'm going to prove. Let's say I have a tangent line on this side and a tangent line on this side, and those two tangent lines meet at a point outside of the circle. Then the relationship is that these two pieces of those two tangent segments that go from their point of tangency to the point where they meet, they must be congruent. So this is the relationship that we have here, that these two segments are congruent as I've marked them off. Okay, so let's go ahead now and prove that these two tangents that meet at a point outside the circle, that those two segments that are formed are congruent. This is the relationship. Let's go ahead and create our proof. So I'm going to come up with another circle. Here's our next circle. Okay, and I'm going to go through the process of proving that. Let's say we have two tangent lines. Oops, I picked the wrong thing again. All right, two tangent lines. Here's one of them. Here's the other tangent line. All right, there are some things that we know to be true already. We already know that we have a segment here and a segment there, and those are radii. And they are congruent because all radii in a circle are congruent. So you have the congruent radii. Radii is plural, by the way, so that's the first thing you'll notice. The second thing that we can put inside of our picture, I'll do it in blue, is that this radius and this tangent are going to be perpendicular per our last problem there. We have two right angles there. Finally, I can place a third segment inside of my picture, going from the center down to that point where the two tangents meet. All right, it's not the best line there, but just work with me. All right, and that third piece that I have there, they are, since we have right angles, they are the hypotenuse of each of those now right triangles. So you have congruent hypotenuses by the reflexive property, right? Because it's a shared side, so they are the same length because it's a shared side, so they're the exact same segment on each triangle. Let me go back up and just point at. So now those radii are more than just radii. In terms of the right triangles that you see here, they're actually legs. So you have two right triangles with congruent legs and congruent hypotenuses. Then these two right triangles must in fact be congruent. Go back. So the two right triangles are congruent by HL. And if they're congruent by HL, then all other corresponding parts of congruent triangles are congruent. There we go, CPCTC. So then finally, this piece here must be congruent to this piece here, just as we set up the relationship on the left. All right, so we're going to actually utilize these two relationships in our next videos, and I will see you then.